Hi everybody, welcome back to the channel. In this video we're going to take a look at horizontal asymptotes and end behavior. Both of those phrases are things that you should have heard before in past classes. But what you probably don't know is that when you talked about horizontal asymptotes or end behavior in past classes, you're actually talking about the idea of a limit. You probably never heard that word in those classes because you weren't talking about limits at the time specifically. But a horizontal asymptote really is a limit. So this section is going to be called limits at infinity. And I'll put a little semicolon and talk about horizontal asymptotes. And I would actually kind of group slant asymptotes or oblique asymptotes into this category as well. Those are both kind of talking about end behavior as well. And so every example of a limit that we've seen so far has had the limit as x goes to a of a function f of x. The difference is in this section we're not going to be using a, we're going to be talking about the limit as x goes to infinity of f of x, or we could be talking about the limit as x goes to negative infinity of f of x. And I will say that this idea of a horizontal asymptote, or the idea of a limit as x goes to infinity, is probably one that's pretty intuitive to you. You probably have a pretty good idea of what's happening. Basically, we're just looking at a graph saying as x gets larger and larger and larger and larger, does your graph approach a specific value of L? So you might say that this limit up here is equal to L. And the limit could be equal to L, or the limit could be equal to infinity as well, which just means that as x goes to infinity, the output value is getting really, really close to infinity. Or whatever close to infinity means. The output value is getting larger and larger and larger. So let's take this first example where the limit as x goes to infinity of f of x is equal to L. The idea here is that as x is getting larger, your graph is just approaching that value, and so we've drawn kind of these horizontal line here saying that these two, your function and your dotted horizontal line there, are getting closer and closer and closer to each other, and eventually the distance between them is getting smaller and smaller and smaller. Essentially, you can get as close as you want to L with your output values as x continues to get bigger and bigger. And then obviously the x going to negative infinity would be talking about maybe over here saying, okay, well, as x values go far to the left, what's happening there as well. Okay, so in this video, we're not going to necessarily talk about the idea of what is a limit in this context. We've already seen what is a limit. So we're really just going to look at a few examples and look at how are things different when we talk about x going to infinity rather than x going to a specific value like a. By the way, it is possible to have two horizontal asymptotes in the same function. It's not possible to have more than two because then you wouldn't have a function anymore, but there are plenty of functions where you could have a horizontal asymptote in one place, another horizontal asymptote for another output value, and you might have a function that does something like this where as x goes to infinity, you get to one value for that horizontal asymptote. You might say one L value, and then as x goes to negative infinity, you get a different output value or a different limit. And that's fine. In fact, a good example of this is something like, I'm not saying this graph exactly is this function, but something like y equals the inverse tangent or the arctangent of x actually has that behavior where you have a horizontal asymptote above the function and you have a horizontal asymptote below the function. And there's actually two different horizontal asymptotes there. Another feature that people often think is incorrect or think about incorrectly is a lot of people think that your graph can never cross any asymptotes. Like we've kind of learned that informally and actually incorrectly when we first learned about asymptotes is that we tend to remember that a graph can't cross its asymptote. That's actually not true. A graph can't cross a vertical asymptote because that means that the function would have to be defined there, but it is actually possible for a graph to cross a horizontal asymptote. Here's an example of what that could look like. Let's say you have a horizontal asymptote where the limit as x goes to infinity of f of x approaches a specific line, and I'll just use as an example 4. So this line is up here at y equals 4. It doesn't necessarily mean, depending on what your function is, it doesn't necessarily mean that your function can't cross this horizontal asymptote. Remember, a horizontal asymptote is just talking about the end behavior. We don't actually care about kind of what happens in the middle. It's really just saying what happens as x gets really, really large or really, really far negative. And you can definitely have a graph that goes up and kind of crosses the horizontal asymptote and then kind of levels out at that horizontal asymptote, as long as the end behavior of that function is still approaching that asymptote. It's perfectly fine for a function to cross its horizontal asymptote. So just kind of a misconception. I thought I'd address that here as well. Just as we talk about horizontal asymptotes, it's good to know kind of what are some of the features that are there and how do these behave. Now let's go ahead and look at a specific example, and I'm going to pull out an example of a rational function. We could be looking at horizontal asymptotes for other kinds of functions as well. You might remember that exponential functions have horizontal asymptotes. This is going to look like 3x squared minus x minus 2 all over 5x squared plus 4x plus 1. Now you might remember something up from past classes about finding horizontal asymptotes. So for example, if I said, does this function have a horizontal asymptote, and how do you find it? Okay, you might remember something about comparing the largest degree on the top and the bottom, and there was something about how when the degree is bigger on the top, you do one thing. When the degree is bigger on the bottom, you do another thing. If you have the same degree on top and bottom, you do something else. And so that's all fine and good to help you remember things, but that doesn't really get at why do things work the way they do, and it doesn't help you necessarily understand the math behind the problem. Okay, so in this problem, you might be able to remember this and say, okay, well, when I have the degree on top, that's the same. You have x squared on top and x squared on bottom. What you're supposed to do is you're supposed to take the coefficients out front of those leading terms and divide them. And so you should get something like y equals 3 over 5. Okay, and you might remember something else about like what happens if f of x was 2x over 4x squared plus 7. What do you do when the degree is bigger on the bottom? You could flip that around, and what do you do when the degree is bigger on the top? But I want to kind of get at the math of what's happening and help us understand why do we only care about the leading degree? Why do we only care about those first terms? Why do we not care at all about the x or the 2 or the 4x or the 1? Those are basically irrelevant in this problem as far as finding a horizontal asymptote. But why? Okay, it really has to do with limits. And so here's what you're actually doing. When I say find the horizontal asymptote, that's a way to phrase it in terms of kind of a college algebra course. In a calculus course, here's the same exact question, but just written in a little bit of a different way. Find the limit as x goes to infinity of f of x. What is that equal to? Okay, that's exactly the same thing as saying find the horizontal asymptote if there is one. In fact, this is a little bit more specific because if there's not a horizontal asymptote, then your end behavior as x goes to infinity would either end up giving you infinity or negative infinity if you don't get a specific value. And so we can answer this in even a little bit more detail by using limits here. Okay, now I'm going to go ahead and take this problem and I'm going to replace the f of x notation here with what f of x is actually equal to. And we're going to see kind of an algebraic way to approach this that hopefully helps make a lot more sense of why do we only care about the leading degree? Why are we only worried about that first term? So here we go. And you might remember from our past videos, we talked about kind of 3 different ways to handle limits. The first way was to try to plug something in if you can, okay? But that's a little bit tricky because in the earlier problems or in a couple of videos ago, we were plugging in a value like a. That's fine to plug in a value like a. What does it mean to plug in infinity here, if we could try that? I mean, basically you're getting a really large number on the top because 3 times a really large number, basically an infinitely large number squared, and then minus infinity, that's a little weird to talk about, like infinity minus infinity. That doesn't make a lot of sense. It's not zero, by the way, or not necessarily zero, I should say. And then what you have, like infinity on the top and infinity on the bottom, and that just gets really weird. It's kind of like having 0 on top and 0 on the bottom. We've kind of already addressed that. We called it an indeterminate form, and so we couldn't really do anything with that. So if you remember the limit videos, we talked about after you try to plug something in, what could you do then? Well, you could try to simplify. Okay, and this one over here, it doesn't really look like you can kind of factor the top and the bottom somehow, so that something cancels, and even then you're still stuck trying to plug in infinity after that. That just gets a little bit weird. So that doesn't make a whole lot of sense. Here's another way we can handle a problem. Specifically, this is only useful when we're talking about limits as x goes to infinity. So I want to just put a little disclaimer on here. Be careful. What I see from students is once I show you this approach and you start to use this a little bit, students try to throw this approach onto any kind of a limit problem. This is really only helpful when we're talking about the limit as x going to infinity. And you'll see why here in just a second. It's legal every other time as well, but it's just not very helpful. So when we're talking about x going to infinity, this is a really helpful approach. Look at the largest degree that shows up anywhere on the top and the bottom. Okay, the largest degree is an x squared. Okay, so here's what we're going to do for this. Go ahead and take the top and the bottom and multiply by 1 over x squared. And that means 1 over x squared divided by 1 over x squared. That is a fancy form of 1. It is always legal to multiply by a fancy form of 1. No issues there. Okay, this is just a little bit of kind of tricky algebra. We might say, how did you know to do that? Well, I'm kind of telling you what to do. Look for the largest degree, multiply by 1 over that largest degree here. Look at what's going to happen on top and on bottom. Okay, on top and on bottom now, we haven't taken a limit yet, by the way, so I'm just going to continue to write the limit as x goes to infinity. But if you were to distribute this, because you can think about parentheses here, if you were to distribute the 1 over x squared into every term on top and then now into every term on the bottom there, what you end up having is something that looks like this. On the top, we're going to have 3 because the x squareds are going to cancel. And then minus, you have an x over x squared, which is the same thing as a 1 over x. And a minus 2 over x squared. Okay, so that's all on the top. Run out of room a little bit here. And on the bottom, we have just a 5. And then a plus, let's see, it's going to be a 4x over x squared. So it really ends up being a 4 over x. And then at the end there, we have a plus 1 over x squared. Okay, now this seems a little bit weird because we're creating fractions. You're like, well, we went from having just one big fraction to now we have like 4 different fractions inside of that fraction. How does this seem helpful? Okay, and the reason this is helpful is because specifically x is going to infinity. So if you think about what happens when you have 1 over x, the limit as x goes to infinity over here, which, by the way, this is another way of saying what's the horizontal asymptote for the rational function 1 over x. It actually ends up giving you 0. And the reason why is because if you think about 1 divided by like a really, really large number, I'll just put like 1 divided by infinity there, is so infinitely small that it's basically 0 there. Okay, so what happens to all of these small fractions? 1 over x, well, that's 0. 2 over x squared. If you ever have a constant divided by something that's getting infinitely large, that's 0. So 2 over x squared is 0. 4 over x is 0. 1 over x squared is 0. Okay, you get a bunch of zeros. Look at what you have left. 3 over 5. Okay, and this is, and maybe I should still carry that limit there. Or we could look at the limit of 3 over 5, but remember one of the limit properties that we saw in a past video was that when you take the limit of a constant, you just get that constant. So even though there's a limit there still, there's no x in what's left here, so you can't say let x be a certain value. That's just a constant there. You just get 3 over 5. So we only care about the leading degrees or the first terms that are there because all the other terms are kind of too small that they're just going to drop off or go away. But the algebraic approach to be able to see that is to say multiply on top and on bottom by 1 over whatever the largest degree is. And then you should have a bunch of fractions somewhere where you just have x's on the bottom. and so it's constant divided by infinity everywhere, those end up being 0, and you're just left over with those leading degrees.